So our next section we're covering is going to be the double and half angle identities. So names are kind of misleading because the double indicates that we're going to start with double the angle. So I'm going to go through what these different identities are, and these ones are pretty straightforward that I can actually go through and prove them. So for the first one, if I want to find sine of 2 theta, we can instead evaluate this just using theta. So this is equal to 2 sine of theta times cosine of theta. Okay. If I'm evaluating cosine of 2 times an angle, I really have 3 different forms I can work with. The first is I can take cosine squared of the angle and subtract sine squared of the angle. Or I can manipulate these, and cosine of 2 theta is 1 minus 2 sine squared of theta. And then I can do a different manipulation and instead show this is 2 cosine squared of theta minus 1. Okay. These ones are going to be really important when you get to calculus 2, if you have to go that far, because you'll use these identities a lot to be able to simplify expressions to do other things with. So with all of these, the reason they're called double angle is because the angle on the left is double the angle on the right. So again, this just helps us out because maybe this isn't an exact special angle, but half of that angle is. Okay. So to show you where these come from, they ultimately just come from those sum identities. Because if you think about what sine of 2 theta is, this is sine of theta plus theta. Okay. And then using our sum identity, this gives you sine of the angle times cosine of the second angle, plus cosine of the first angle, sine of the second. But really, it's the same angle in both, so it doesn't matter the order. In total, you have 2 sine of theta, cosine of theta. Okay. For the cosine, they just come from the cosine formulas. So again, 2 theta just means you're taking theta plus theta. So this gives you cosine of the first angle, cosine of the second. The sign switches, and then we get sine of the first, sine of the second. But since it's the same angle, cosine times cosine is cosine squared. So this gives us cosine squared of theta minus sine squared of theta. Okay. The others just are a manipulation of this form. So what I can do is use my Pythagorean identities. Cosine squared is 1 minus sine squared. So subtracting an extra sine squared means you're taking 1 and subtracting 2 of those sine squareds. And likewise then to get the last identity in terms of all cosines, sine squared is 1 minus cosine squared. That minus minus distributes and you get plus another cosine squared. So you end up with 2 cosine squared of theta minus 1. Okay? So those are our 4 double angle identities. Again, as long as you know your sum identities, you can easily derive these. So it's not necessary to go through and memorize every single one of them. So let's go ahead and try a couple examples involving this. If we know cosine of theta is equal to 3 over 5, and theta is between 0 and pi over 2, we want to find sine of 2 theta. So again, 2 theta is an angle I know nothing about. However, sine of 2 theta is 2 sine of theta times cosine of theta. Okay. I know cosine of theta. I need to figure out what sine of theta is. So I want to find sine of theta. And if you consider this angle, theta is in quadrant 1, so sine is going to be positive there. Make a triangle if you want. I'm going to go ahead and use our Pythagorean identity. Cosine squared plus sine squared needs to equal 1. We know cosine is 3/5. So 3/5 squared plus sine squared is 1. 3/5 squared is 9/25. So subtracting 9/25 gives us 16/25. And then taking a square root, we only care about the positive case. So sine of theta is going to be 4/5. So our exact value of sine of 2 theta is going to be 2 times sine of theta times cosine of theta. So multiplying that out, 2 times 4 is 8, times 3 is 24, and in the bottom, 5 times 5 gives us 25. So again, without even needing to know the angle itself, I know that sine of 2 theta is going to be 24/25. If I want to find cosine of 2 theta, again, you have a ton of different formulas that you could use. You can use that this is cosine squared of theta minus sine squared of theta. You can use that this is 1 minus 2 sine squared of theta. Or this is 2 cosine squared of theta minus 1. Okay. In reality, any of these work because you know sine of theta, but if that wasn't part of the problem, you know cosine of theta is 3/5, so it would make the most sense to use the formula only involving cosine. Okay. So cosine of 2 theta is 2 cosine squared of theta minus 1. And cosine of theta, they tell us, is 3/5. So simplifying that out, that would give us 9/25. So we need to do 2 times 9/25 minus 1, which gives us 18/25 minus 1. And that's minus 25/25. So this will be negative 7/25. Okay. If I want to find the exact value of cosine squared of 105 degrees minus sine squared of 105 degrees, well, 105 degrees is not anything I know at all. So I'm going to see if I can relate this to something else I do know. And if I look at the way that is given to us, this is cosine squared of an angle minus sine squared of an angle. That's exactly one of my identities. This condenses to cosine of 2 times that angle. So when I'm looking at evaluating this at 105 degrees, double that angle is something that's nice. 2 times 105 degrees is 210. And that is one of our special angles. So just to draw a little picture, this is 0 degrees, this is 180. So 210 is right here, which goes an extra 30 degrees out. Okay. So I'm using a 30-degree reference angle, which means I'm dealing with √3/2 for the cosine function. I'm in quadrant 3. So the exact value of this would be negative √3/2. Okay. So those are our double angle identities. What we can do is we can really utilize this to find a bunch more. So again, these ones aren't necessary that you have to remember. It's just a matter of manipulating these. So I know that cosine of 2 theta is 1 minus 2 sine squared. So if I rearrange this, I can go ahead and solve for sine squared. I would add this to the other side and then move the cosine over. So just kind of flip-flopping this. tells us 2 sine squared of theta is 1 minus cosine of 2 theta. Okay. And then dividing by 2 gives us sine squared of theta is going to be 1/2 times 1 minus cosine of 2 theta. Okay. So this is another identity that might come into use for us, but it helps us be able to reduce this. Okay. Then doing the same thing with cosine of 2 theta, solving for the cosine squared, we flip those orders. So that gives us 2 cosine squared of theta is equal to 1 plus cosine of 2 theta. Dividing by 2 gives us cosine squared of theta is 1/2 times 1 plus cosine of 2 theta. Okay. So a second identity just from manipulating our double angle. Those are also very important in calculus 2. You'll refresh over them there. But the nice thing is it takes a square function and then makes it just a singular function, which is always nicer to work with. Then if I want to find tangent of 2 theta, this again just comes from that same identity. So if you think about tangent of theta plus theta, you get tangent of the first angle plus tangent of the second, 1 minus tangent of the first times tangent of the second. So simplifying that a little bit tells us tangent of 2 theta is going to be 2 tangent of theta over 1 minus tangent squared of theta. So this is the double angle identity for tangent. But then you can also work with tangent squared. Tangent squared is sine squared over cosine squared, and then filling in what sine squared and cosine squared are. The 1/2s cancel each other out. So in the same way, we can take tangent squared and we can get rid of the squared. And this gives us 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. So again, more identities that just result from manipulating our sum and difference identities. These then lead into what's known as our half angle identities. So again, going back up here, these are double angle because the angle is double what's on the left. Now our half angle identities are the angle on the left is half of the other angle, okay? So really from here, to get sine, you would take square roots. The problem is, again, when you take square roots, you get plus or minus. So sine of theta is going to be plus or minus the square root of 1/2 times 1 minus cosine of 2 theta. Cosine squared of theta is 1/2 1 plus cosine of 2 theta. So again, you take a square root, but anytime you take a square root, you get a plus or minus, okay? And then from this last one, same thing. Tangent of alpha or tangent of theta is going to be plus or minus the square root of 1 minus cosine of 2 theta over 1 plus cosine of 2 theta. Okay. So these are half angle identities. The other way you might see these is you can replace this by theta over 2, or to avoid confusion, let's use alpha over 2. So what happens is this angle doubles to get the one on the right. So this would be plus or minus 1/2 times 1 minus cosine of alpha. So that's another way you might see it, which is why it's called the half angle identity. But again, I personally don't like using this form. I like instead just working with the double angle identities and manipulating them to get what I want. So the problem with doing these is you have this plus or minus that's out front. So remember, the quadrant you're in is going to tell you whether sine, cosine, or tangent is positive or negative. So you're going to need to do some extra information to figure out, do you take the positive version of this formula or do you take the negative version of it? So let's try some examples with this. We're given that cosine of 2 alpha is negative 2/5, and pi over 2 is less than 2 alpha, which is less than pi. We want to find sine of alpha, okay? So again, I'm going to utilize my formula to figure this out. I don't like memorizing those half angle identities, but this is one that has stuck in my brain. Sine squared of alpha is 1/2 times 1 minus cosine of 2 alpha. Okay, so I have this piece here. So if I just want sine of alpha, I'm going to go ahead and I'm going to take a square root. Okay, well, if I know what quadrant alpha's in, I know whether to take the positive or negative case. Okay, so they tell us that 2 alpha is between pi over 2 and pi. Well, if I divide everything by 2, that tells me alpha is between pi over 4 and pi over 2. So thinking about where that is in our unit circle, pi over 4 is 45 degrees, pi over 2 is at 90, so alpha is in quadrant 1. Okay. So when I'm finding sine of alpha, I only care about the positive case. Okay. And now I can just utilize my formula and simplify it. Cosine of 2 alpha is negative 2/5. So this becomes the square root of 1/2 times 1 minus negative 2/5. Well, minus minus turns to plus. So that's going to be 1/2. 1 plus 2/5. That's going to be 7/5. And so that gives us the square root of 7 over 10, which you can rationalize, but for time's sake, we're not going to. So the exact value of sine of alpha is going to be positive square root of 7 over 10, okay? So again, you're always going to be given information about one of the angles to know whether you're taking the positive or negative case. You just might have to do some manipulation. So 2 alpha was in quadrant 2, but alpha then is going to be in quadrant 1. Okay? If they told you something else, like maybe alpha was between 3 pi or pi and 3 pi over 2. If you then found alpha, you'd have pi over 2 is less than alpha is less than 3 pi over 4. Well, in that case, that would be pi over 2 is up here, 3 pi over 4 is halfway in between, so your angle would be in quadrant 2, and that tells you whether to take the positive or negative case. So in that instance, if you were finding cosine of alpha, you would use the negative version, okay? Let's try another example. We want to express the function cosine of 4x as a trig function of just x. So our goal is to get the argument using an x. Okay. So this is where we're going to use one of our identities, because what happens with our cosine of 2x formula is the angle is going to half when I use one of my identities. And I'm going to use that cosine of 2x is 2 cosine squared of x minus 1. So the angle halves with the formula. Okay. So if I'm starting with cosine of 4x, applying this formula gives us 2 cosine squared minus 1. And this angle is going to half. So the inside argument is going to be 2x. Okay? So unfortunately, that doesn't give my inside argument to just be x. So realistically, what I'm going to have to do is do this again. Okay? You can think of this a couple different ways, but this is basically cosine of 2x to the second minus 1. So what I need to do is I'm going to need to square this right-hand side. So that gives us 2 cosine squared of x minus 1. And then I'm going to square it. So this is fantastic because now I have an argument of just x instead of 4x. So I'm just going to keep going with this. I do want to simplify this out. If I square those pieces, you get the first term squared. So you get cosine squared squared. So you get cosine to the 4th of x. Then you get 2 times the product. So that would be minus 4 cosine squared of x. And then plus the last term squared. Distributing out the 2 gives us 8 cosine to the 4th of x minus 8 cosine squared of x plus 2 minus 1. And then combining that last piece, plus 2 minus 1 just gives us plus 1. So that is my trig function solely involving x. Okay? All right. The last formulas we have are product to sum and sum to product. They are a bit messy, so again, these are not something that you're typically expected to remember. I'm going to go ahead and I'm going to write down the formulas, and then I'm going to show you how to prove one of them. The others follow in a similar manner, but it just makes it easy if I'm taking the product of two trig functions. I can instead turn it into a sum. So if I'm taking sine alpha times sine of beta, this is going to end up equaling 1/2 times cosine of the difference of the angles minus cosine of the sum of the angles. Okay, so again, it turns it from a product of trig functions to a sum of trig functions. If you do cosine alpha times cosine of beta, this turns to 1/2. And really you end up with the same thing. You get the difference in the two, but now you're going to add cosine of alpha plus beta. Okay. So when it's the same trig function on each side, you have the same formula on the right. When it's different trig functions, this is going to involve sine. So it's 1/2 sine of alpha plus beta plus sine of alpha minus beta. Okay. So what I'm going to do is I'm actually going to show this first one, and then the others are going to follow in a really similar manner. And so I'm actually going to work with this expression over here and show you it reduces to just sine of alpha, sine of beta. Okay. So if you think about what cosine of alpha minus beta is, that's the difference of the two. So this gives you cosine of alpha times cosine of beta. Then we get plus sine of alpha, sine of beta. Okay. If I consider the opposite, cosine of alpha plus beta, you get the same thing, but this is a minus instead. Okay. And what I want to do is I want to end up with these. So I'm actually going to subtract the two quantities. And so what that does is it changes both of those signs. So on the left-hand side, we're going to get cosine of alpha minus beta minus cosine of alpha plus beta. These two cancel each other out, and then those are exactly the same, so you get sine of alpha, sine of beta. And then to get this on its own, we just divide by 2. So this tells us sine of alpha times sine of beta is going to be 1/2 cosine of alpha minus beta minus cosine of alpha plus beta. Okay. If you want the second formula, all that comes from instead is adding these together. So that makes this positive and this negative. Those would cancel, and you have 2 times that quantity. So they all follow in a really similar manner. So let's try a few examples of this. We're going to write the expression as a sum or difference of trig functions. So here I am multiplying 2 different functions, the sine function and the cosine function. So this is always going to always be multiplied by a 1/2. So we start by doing sine of the sum of these angles. And then we add sine of the difference of these angles. And then filling that out, 40 plus 88 is going to be 128. And 40 minus 80 is going to give us negative 48. And then I don't like a negative angle, but sine is an odd function, so that minus just pops out. Okay. And so we're able to write this expression as a sum, in this case, difference of trig functions. Okay. For the next one, I'm multiplying sine and sine. So the 8 just stays out front. When I multiply sine of 5x times sine of 6x, you end up with 1/2. And then I'm going to get cosine of the difference of these angles. And then plus cosine of the sum of these angles. 8 times 1/2 gives us 4. 5x minus 6x is negative x. And then 5x plus 6x is 11x. And then again, really don't like that minus sign, but cosine is an even function, so we can get rid of it. Okay. So those are the product to sum formulas. The last special formulas we have are then the opposite. We're starting with the sum and turning it to a product, okay? So in this case, it's kind of just the reverse. Those formulas, again, follow just from manipulation. We're not going to sit here and prove these. Again, these are not formulas you're going to likely be expected to remember. So I want to turn this from the sum of 2 angles or 2 trig functions to the product. So when I'm working with sine of alpha plus sine of beta, this turns into 2 sine of, we're going to average this angle, alpha plus beta over 2. And then we get cosine of the difference, alpha minus beta over 2. Okay. If I'm subtracting, it really is almost identical. We just switch which angle goes where. So this is alpha minus beta over 2, and this one will be alpha plus beta over 2. When we're dealing with cosine, then you're going to get the same function on both of them. So cosine of alpha plus beta keeps the same function. So this will be cosine of the average of the two angles. And then the same second angle, alpha minus beta over 2. If you do cosine of alpha minus cosine of beta, this will deal with sine, and it ends up being -2 sine of then the same two angles. Okay. So again, not formulas that are super, super common, but they are relevant in some instances. So we're going to just try a few examples of this. We want to write the expression as a product. So I have cosine of an angle minus cosine of an angle. So to turn this into a product, we're using this last formula. That gives us -2 sine of we add these angles together and then divide by 2. And then we subtract the two angles and divide by 2. Okay. So this gives us -2 sine of 8x over 2 sine of 4x over 2. And then simplifying that gives us sine of 4x, sine of 2x. Okay. So we've turned the difference of two trig functions into a product instead. Now let's do the same thing, but involving an actual angle. So here we've got sine of 35 degrees plus sine of -56. If you want to pop that sine out to begin with, because sine is an odd function, absolutely go ahead. You'll end up with the same thing. But if you don't want to do that, we can just jump into our sum to product formula. So for sine, you get a 2 out front, and then you get opposite functions. In the case when we're adding, we start by adding and dividing by 2. And then in the second one, we are subtracting and dividing by 2. So that gives us 2 sine 35 minus 56 gives you -21 over 2 degrees. And then the minus turns to plus, so 35 plus 56. That gives us 91 degrees over 2. And then again, to clean this up, we can pop that minus sign out because sine is an odd function. So you end up with 21 degrees over 2, cosine of 91 degrees over 2. You can write it with decimals if you want to. You can do 10.5 and then the 45.5. But if you left it like this, that's fine too. Okay? So these are a lot of our main identities. What we still have left to do is we need to talk about solving trig equations and then also working with inverse trigs functions.